Hello, my name is Marco Riani.
And my name is Anthony Atkinson. We would like to present results from the second chapter of our new book about regression, which is jointly written with Aldo Corbellini, Domenico Perrotta, and Valentin Todorov. In the first video for chapter 2, we discussed theoretical methods of robust estimation, or theoretical properties of methods of robust estimation, and used asymptotic results to compare the different methods. You will recall that a basic tool of estimation depended upon the rho function, which downweights extreme observations. Our conclusions was that the actual rho function chosen did not really matter very much. In this video, we look at practical applications of robust methods. We've used simulation to find out what happens when we do not know the values of some of the parameters that we are trying to make inference about.
First of all, we want to see how the different estimators behave when no outlier is present in the data. Here we consider a simulation studies where we have 50 replicates, and each replicate is based on a sample of 200 observations coming from the normal distribution with mean is equal to 5 and standard deviation equal to 2. We show for the 50 simulations the values of the estimate of mu in the upper panel, the values of the estimate of sigma in the lower panel. The black horizontal line refers to the true value of the parameters.
In the upper panel, the estimate of sigma squared is found using the normalized MAD. The very jagged nature of these figures is not of importance. This is just the result of taking the same sample and subjecting it to several estimates. We're not interested in whether they are all up or all down at a particular point. What we are concerned about is whether they move up and down together.
In general, all these rho functions produce very similar estimates. Maybe the only one rho function which produces estimates which are slightly different from the rest is the optimal rho function. You can see that it has slightly different behavior sometimes.
In the lower panel, we are concerned with the estimation of sigma, and we have assumed that the value of mu is known. These curves jump up and down just like the ones in the upper panels, but now there is really very little difference between the algorithms.
Now we move to figure 2.23. The purpose of this figure is to understand and appreciate the effect of two possible contamination schemes. In the literature of robust statistics, you have the shift contamination, where a fraction of the data is contaminated adding a certain constant, and you also have the point mass contamination. In this second case, a fraction of the observation becomes equal to a particular number.
We would like to stress that this is the literature for robust methods, and these are scenarios which are used to test particular procedures. They're considered to be the two most extreme. Of course, in a robust analysis of data, the pattern of outliers and contamination can be of any kind you care to imagine.
In both panels we have the estimate of location. The top panel refers to the shift contamination. On the other end, the bottom panel refers to point mass contamination. In both panels, the estimates have been ordered according to the values of the Tukey by weight estimates. From the top panel, you can see that there is an agreement between the different estimators that maybe there is a higher variability for the hyperbolic estimators. You see that there is a higher variability here with respect to the other estimators. In the bottom panel,
the blue line is the trace of the ordered Tukey values, so they increase monotonically in a nice, smooth way.
We can see particular strange behavior for the optimal rho function.
This starts off sloping upwards pretty much like the other estimates, but and at the very high values, or even from halfway up, it is horizontal. There's very little change with regard to the Tukey, but in between the two, there is a period of oscillation, sudden and violent oscillation, between these two possible estimates. So really, this is almost as if it were providing a binary estimate of the parameter. The other difference is the optimal rho function, which seems to have a slightly higher value than the estimates contributed by the other estimators.
At the end, the behavior for power divergence and ample and hyperbolic seems to be very, very similar. Now we move to figure 2.24. The purpose of this figure is to show the effect of using in the estimate of location a parameter sigma which is known, left panel, or a parameter sigma which is estimated, right panel. In both cases, we consider the estimate of location. And once again, the black horizontal lines refer to the true parameter value. In both cases, we have 30% shift contamination. It is clear that if you use the true value of sigma, the estimates are centered around the true value of location. On the other hand, if you use an estimate of sigma, in this case sigma is estimated using the normalized MAD, the estimates of location are biased. The message which comes from this plot is that in the context of robust estimation of location, it is important to have a good estimate of the scale. Because if you don't have a good estimate of scales, you end up with a distribution of parameter estimates which are biased. Finally, notice that while these different rho functions have a similar behavior, there is one exception, which is the hyperbolic, which shows some outlying estimates for location. Finally, notice that the optimal rho function has a Bose plot which is much larger than that of the other estimators.
It should perhaps be stressed that for ordinary least squares estimation, the estimate of mu, the location parameter or the regression model, is independent of the estimate of sigma squared. This is absolutely not the case for robust regression.
Now we move to figure 2.25. Here we consider a simultaneous estimation of mu and sigma. In the top panel, you have the distribution of the estimates of location. In the bottom panel, you have the distribution of the estimates of the scale. Once again, the horizontal line refers to the true parameter value, the true location for the top panel and the true value of the scale for the bottom panel.
The top panel shows that there is little effect of the rho function on the estimates of location, and the box plots are nicely centered around the value of 5. The story is very different in the lower panel for the estimates of scale. They are all biased, and there isn't really very much difference between the estimators, except perhaps for the hyperbolic, which is slightly more biased than the rest.
In this case, we have considered a 10% point mass contamination. On the other hand, the value of the breakdown point which was used is 0.5. So very different from the true contamination level. Now we want to repeat this plot, but now we consider a value of breakdown point equal to 0.2. Let us put together these two figures.
The top rows give the comparison of the estimation of mu In the left-hand panel, the estimates are for a BDP of 0.5. In the right-hand panel, the BDP is 0.2. Both are very much unbiased if you look at the centers of the thing of the box plots. But in the right-hand panel, the variance of the estimates is less because we are using more of the observations in the robust estimation.
Finally, notice the distribution of the estimate of scales. Then here you can see the black horizontal line which refers to the true value of sigma. Here you cannot, or well, it is down here, it is hidden. So this implies that it is better to use a higher value of breakdown point to estimate the scale, but the point is that if you use a higher value of breakdown point, you have a greater variability of the estimates. So if you want to do simultaneous estimation of mu and sigma, it is better to use a higher value of breakdown point. But this higher value of breakdown point is counterbalanced by the fact that the estimates have a much greater variability.
In Chapter 3, when we get on to robust regression, we will be comparing several procedures that have been suggested for the estimation of sigma squared when the mean is being estimated by a M estimation using one of the row functions we have discussed here.
Now we move to figure 2.27, and the purpose of figure 2.27 is to understand the effect of two different values of breakdown point. In both cases, the sigma which is used is the true value. In the left panel, we use a breakdown point of 0.5. On the other end, in the right panel, we use a breakdown point of 0.15. As you can see, the variability of the estimates when the breakdown point is smaller is much more reduced. In this example, we have considered in both cases a 15% of contamination. Note that here the right panel has a value of breakdown point which is 0.15, which is exactly equal to the fraction of units that have been contaminated. And this also suggests that if you use a breakdown point that is very close to the true fraction of contaminations, your results are very good.
But despite the advantages of using the correct value of sigma in your estimation, if you have to estimate it as well, things are, as figure 226 shows, rather different.
The final point that we want to touch is the issue of multiple solutions. That is, if you have estimators which have a redescending psi function, it may happen that you end up with a series of local minima. In this example, in order to show this issue, we consider the first 20 observations for the first dataset, and then we have 3 contaminated observations, and then we check whether there are or not multiple solutions. Here in figure 2.28, we consider the 6 raw functions, and we can see that while for the Huber raw function we have just a single intersection with the horizontal line of 0, in the other cases you have generally 3 intersections.
In this particular example, this is not the case of the power divergence row function, but it may well be for other data sets. The solution to this problem is to estimate the parameters several times and to take the minimum value of the objective function that is obtained.
Let us come to the conclusions for this chapter. In the last 20 or 30 years, the interest was in finding the best raw function. On the other hand, the focus on this book is to understand the effect that the inclusion of new units has on your estimate. We have seen from this systematic comparison, asymptotic and small sample comparison, that maybe apart from the optimal raw functions, all the other functions have a very similar behavior, both asymptotically and non-asymptotic way. Therefore, it is not an issue the raw function which is used. It is important not to use a single prefixed value or point or the efficiency, but it's better to understand how your estimates change as your breakdown point and efficiency changes.
This general idea of looking at a fits from a sequence of parameter values is one that we pursue throughout the rest of the book.
Thank you for watching and see you to the next video.
Yeah, ciao, ciao.